Okay, let's get started. So we will continue looking at EM structure simulations today, and hopefully this will be the last of the basic introduction to this. We'll of course come back to it again when we look at more specific structures. So in the last class, we looked at the microstrip simulations in a little bit of detail. Then I very quickly showed you the strip line and the CPW structure. So we'll go through those two things, and I'll tell you a few more sort of tricks and tools on how to use these EM structure simulations effectively so that we can use them for analyzing actual devices later on. So I hope you're all trying these things out at home after the classes so that we can start using them effectively. Because very soon we will kick into much faster gear after Diwali, and we'll cover things quickly. So you need to be able to do these things in the microwave office effectively. So just as a reminder, here is the microstrip EM structure. The enclosure for that looks like this. The dielectric layer, as I tell you, gives you the cross section. And in this version of AWR, which is I'm running on a much more powerful computer bit, the standard units are specified in millimeters. So just take note of that. So that's why I specified the as 0.762. And this is the TMM6, which I already defined. And since this is a microstrip, we have a perfect conductor at the bottom, then the substrate, then some amount of air for 2 millimeters. Then we keep that as proximity. So as I mentioned, the top boundary here can make a difference if this thickness is very small, so the background plane is close to your active metallic conductors. So in this case, it shouldn't really matter. And this TMM6 was defined here. Just a very quick reminder. I've also chosen a much coarser enclosure spacing. So this is about 50 microns for the grid spacing, so that the simulations start fast. Actually, I checked it this morning. This computer is very powerful, so it's transferring. But I've made it much coarser. But one of the things you can check always is to reduce the resolution or increase the resolution and see if the overall results are changing much. So this is a very standard technique in any numerical methods, because you always have to choose some step size, either in spatial dimensions or in time dimensions if you're solving some kind of a differential equation. And how do you choose what's the optimal step size? Right? Because the finer it is, it's always better. So it's a compromise between accuracy and the time it's going to take to solve. So same way here. But as I mentioned, the grid spacing is only loosely connected with the actual mesh size. It will automatically determine the optimal mesh size. But generally, if you make it very coarse, it's not going to make it finer than that. So that sort of sets the lower limit. So you can go very fine, but it may not do it. But you will see, you will try some of these things just a little bit. So then I've already drawn here a microstrip whose length is about 5 millimeters and the width is about 1.1 millimeters. So let's just go back to TX line, double check this. So this is 762, electric 6. Set to this as 1100. That's basically close to 50 ohms. So this is the right set of parameters. Go back here. I've already made some graphs here, but currently the microstrip EM structure, you can see it's a little grayed out compared to the CPW. That means I've disabled it so that I can not run all the EM structure simulation at the same time. So you do change that from here. So toggle here. Book here. disable that. So right now, only in the microstrip simulation is active. So run that. Stop. So here is scattering parameters S21 transmission and S11 the reflection. Please note it's in dB units. You should also get used to seeing these numbers. So unit transmission means 0 dB log units, and this is sort of orders of magnitude. So the reflection is near minus 30 dB or below, which means this is 10 minus 3 or lower. So these are very, very small numbers. So it's good. So basically, this is 1 and this is effectively 0 if we look at the linear units. This is something to get used to, because sometimes when we look at certain structures, if they are of some finite length or several wavelengths long, even just a simple transmission line, and we will see one example a little bit later, you might see some features in the reflection. So for example, even here, if you see at low frequency, it's less than minus 40, and at around 7 gigahertz, it's minus 30, and it's going through this maximum and then going back down. This really doesn't mean much, okay, in terms of a practical performance. Because this is, we are talking about whether it's 0.001 or 0.0001. Okay. Practically, it makes no difference. But there is a reason why this is happening. It's because I can never make an exact 50 ohm transmission line using any NPN structure. So it's always going to be off slightly, which means you're going to get some reflections at each end, but they're going to be very small. But the numerics here is accurate enough to capture that. So just to illustrate what I mean by that, I'm going to take this microstrip. I'm going to make it much larger, make it like increase it by another 20 millimeters. It's very long now, so that it's several wavelengths at the relevant frequencies. I'm going to run this. This is what I meant by that. This is a perfectly fine 50 ohm transmission line. And you will see these kind of responses even when you measure real transmission lines in your lab using, say, a vector network analyzer. And what is happening at these points is some interference condition is giving you zero reflection, right? Some kind of effective impedance transformation is going on because your loads on either side are 50 ohms. The transmission line is not exactly 50 ohms. So you know this will happen at lambda by 2 of integer multiples of lambda by 2. And then it has one burst points which are also periodically separated. But everything is below minus 30 or so. So absolutely no problem. The reason I'm emphasizing this that I've seen this while teaching this in the past or training students in my lab, that you look at these features and try to make some meaning, because on the log unit, everything looks exaggerated. So we can't really make much of this. These are very, very small changes. So that's just the revision for the microstrip. Now, let's just maybe disable the reflection part. So now you also see this thing which I pointed out last time. There's a lot of these features, but these are all very small, and in fact, it's even going above 0. Right? So these are due to small numerical inaccuracies, nothing to be worried about from this point of view. Unless these become very big, then you have a sales problem. It's very small. But what I'm going to do is I'm going to look at the same simulation and see if changing the grid structure makes this that changes this features. I'm actually going to make it worse, make it less, more ports or less resolutions. On this thing. So what you saw right now in action was this interpolating effect which the software is trying to do. So it solves for a few points and then tries to match the solution. So you see that this new solution, exactly the same structure, has, if I follow this overall trend, it looks similar, but now there are these additional features here. But again, very small, really doesn't mean much. Let's freeze that as well. Now let's make it more accurate. So I'll go to 10 micron. So this one might take a little bit more time, but not so much. So it's become slower because I've made the grid smaller. So it's trying to use a smaller grid space. So you see it has only computed a few points, but it has guessed some curve and it's adding more points and adjusting it real time. Can't really say which one looks more accurate, except that now there are less regions where maybe it's above 1. But point to note is that all of these are very, very small. So you will see this kind of behavior. You have to make a judgment call on whether this is something to worry about when you're interpreting your results. So let me go back to something more reasonable. Let's look at the reflections. To keep it in this resolution. So as I mentioned last time, this advanced frequency sweep itself can cause some problems sometimes, but this is just a simple transmission line. There's not much going on. The response is expected to be smooth. So interpolation works pretty well. So even though I have specified the frequency as 1 to 10 with 0.1 steps, so 91 points, it's probably solving maybe 10, 20 points at this, maybe less. Then it uses those solutions to stitch the solution. All right, so now let's move to strip line. Even though technically I don't have to do that, because unless I change the structure, so it has this feature that unless it notices that the structure has changed, it always checks the solution it has in memory is still valid. So it wouldn't run it again, but just for safe. So like we saw last time, the strip line on this screen doesn't look any different because it's still just a metallic strip going from one end to the other end. The difference comes in the enclosure. So we go to the dielectric layer now. So the top layer is no longer air, it's now the same material gaining 6. It has the same thickness 0.762. Then there is the top layer boundary is also being changed to a perfect conductor. So this is basically the straight line geometry, and everything else is the same. Of course, I've chosen this width differently, so that again comes from line. So let's open that. It's already defined that 6. The thing to note here is how in TX line the height is defined. So it's not defined as half the height, which is the way we have defined. It's the total height. So the height mentioned here is 762 times 2. I made this mistake in the morning when I was checking. And then I found that for 50 ohms, you need something like 443 ohms for the width. That's what I made here. It's not exactly 443 because the resolution is smaller. I've chosen 450, just close enough for this. So now I go to the straight line, plot this relation. Already solved. Force reseparation. I just deletes the data, it's already has the data. So again, transmission close to 0 dB and reflection below -20. Here. As I mentioned, -20 is sort of the rule of thumb we use as something that's good enough. But this probably can be made better because I have not chosen. So we can see if adjusting the width of the transmission line so makes any difference. And notice this is a smaller length, so you're not seeing the many periods. I increase the length for the microstrip. This one is only 5 millimeter long. So again, this period you're seeing is exactly the same effect. I make it smaller by 50 microns. It's 400 microns. It's clearly worse. And here it's for checking fine stuff. The reflection is for the same reason, it's a much better indicator of what's going on. You won't see much of a difference in the transmission rate because this is still has gone from slightly below 0.01 to slightly above 0.01. You're not going to see much in the transmission. So that won't work. Let's go back here. So the only other option we have is 500. So we already tried 450. That was our reference curve. Yeah, this is much better. So this is again something you will notice that the numbers given from TX line might not exactly match with EM structure simulation. That said 443. Now clearly 500 is further away from 443 than 450, which we had tried. But here it seems to indicate that 500 is better. But it should not be too far off. So freeze that and just try one more length, which is 550. Press that button. So it's very small amount of change over here, but here it's not. So that's basically good. You see, this is very small change at the end. Otherwise, it's mostly the same. So we are in a good place in terms of the. All right. So now we move to CPW line. So we saw how to draw this last time. So again, there's three metals. Just to refresh, the enclosure looks the same as the microstrip. There's only dielectric on the bottom, and there's a conductor here. The top conductor is not there. So this is going to be CPWG because there's a ground plane underneath. You will check the other version as well. Just change this one. And then I told you that in order to specify the ground reference, you have to put ports on the two ground planes and specify them as -1 on the one port and -2 port. So that gives information to microwave office to excite this correctly. So earlier we saw that in the 3D version you had seen these ground reference connections going above and below. This one does differently, and the auto thing doesn't work. I still haven't figured out exactly why that is the case, but this seems to work properly. So what I mean is this A shouldn't be there when you're doing CPW simulation. That comes by double clicking the property and choosing this type here. So instead of auto, you choose none. So now go back to the X line. Let's look at CPW ground. Height is 762. I've chosen a gap of 100 here. So it's going to enter 50 on this side of the with this. It's about 300. Gap is 100. That's what I've drawn. Here from the grid, you can easily see that it's 100 microns, right? Because it's a 50 micron grid. This is 500 microns. So that's the width of the ground. That is actually relevant. This is set at 350. That's what it's saying. 95. Okay, so we reduce this. 300. We now have a problem because of the resolution. Oh no, okay, it's fine. Let's have to delete this one. Right. Gap of 100. Oh. This one is much worse. Seeing that out here, it's already coming to -13 dB. So we said we want to keep things around -20. So clearly for the CPW ground, this is matching with the DX line is not that great. Go back. Fix it. need this marginal flows of that. So let's try this. So here we might have a problem because of the resolution. So we have only kept 50 microns. We can change it if it's needed. Take a bigger jump. Just do 500 microns. So it's a bit odd. We're already at 500 or 100 gap, whereas CPFD ground simulation here said the width should be 300. There is a significant difference. I think I have potential reason why this might be, but I'm not 100% sure. But that's something we're going to try anyway. So, what happens for this gap? We try the fix this as well as difference. And now try CPW. Put the enclosure and make this approximate. What kind of effect it has? Whatever it has. We just remove the ground from underneath the structure, right? So I went to the enclosure, and the bottom boundary used to be the perfect conductor, so that there's a metal. Now I made it approximately open because the CPW ground versus CPW, that's the difference, right? So the CPW ground has a ground plane underneath the direct, so which means you can now have capacitance between the top and the bottom plates. Whereas in this geometry, there's only capacitance between the lateral plates. Of course, the dielectric is still there, so field lines will penetrate, but there's no metal over there. So we saw this earlier that effectively what it means is that if you have a ground plane, there will be more capacitance per unit length. So for everything identical, you would expect the one with the ground plane to have lower impedance because the capacitance per unit length is higher. So we can sort of verify that here, that the reflection has become worse when I did this. And that's consistent with the fact that I was initially having to increase the width of the central line to make the reflection better, which means I was making the impedance lower, but by removing the ground plane, the impedance has become higher, so it's slightly worse than the CPWG case. But these things will really depend on the presence of the ground plane underneath, will depend on the gaps. Gaps are very small, and your dielectric is very thick, then it doesn't matter so much. So maybe we can test that now. So I'm going to make this, first let me change the grid to 10 microns. So a little bit. I'm going to make the gap 10 microns. First should compute. Should be 762. That's in. So this actually won't work because the gap is so small that I'm not able to get the impedance to be small enough. So even for a 10 width, it's coming out to be 35 ohms. So I can't get 50 ohms. Need the gap to be strong because of the ground. Just give me a second. We do this routinely. Probably the choice of the mistake here. So, okay, this is a practical issue. The dielectric material, the substrate I have been using so far for modeling is a circuit board which we use for making typically bigger size structures. Okay, so it has 762 micron thickness and there's 35 micron thick copper because we typically make structures very big. Now, if my gap is only 10 microns and my height of the metal film is 35 microns, so you see that the thickness now starts to play a big role in the overall structure, whereas these simulations are actually meant for more planar type of circuits. So we never make 10 micron gaps in this particular circuit board. I was thinking of the other kinds of chip we make, where usually the thickness of the film is only 100 nanometers. So then you are much better. It's again a plane, 10 micron gap, 100 nanometers or 0.1 micron thickness. So here the impedance was so low because your two lines are now looking like big sort of 3D plates which are next to each other, right? Because this is only 10 micron gap, but your thickness is about 35 microns. So that forms a very nice parallel plate capacitor going across your length. So that's why it was not going to very low numbers. But the moment I reduce the thickness to 1 micron, it does. So it uses that thickness in some effective way, but that's of course would have been an unrealistic situation. So let's try it with 1 micron. It will not make any difference on the EM simulations because that assumes everything to be infinitely thin anyway. But we need a better way to calculate it in DX9. So 50 micron width and 10 micron gap should give us something for years. So that's here. Further. last check. So this simulation might take a little bit longer. This is under 20, so this is not bad. This one was done with closure with no ground. If I go to the ground on now. So now you see there was hardly any difference because most of the capacitance is coming from the very small gap, and 762 microns is too far away for that ground plane to make. And this one is a lot closer to what we calculated. Right? That is for 50 and 10, and that is 50, and this is pretty close to that, as opposed to the previous one where we had much larger gaps. So I have mentioned this casually, probably 2 lectures earlier. In that previous CPW, that difference between the TX line and the electromagnetic simulations, any ideas why the mismatch was so high? It was almost like 200 microns different on a 300 micron answer. So it said 300 and we had to go something like 500. And as of now, I have a guess, but I could be wrong. But do you remember something I said about the CPW, which could be the reason here? I'd said some very important thing about CPW, which also connects to another type of transmission line, which we don't use much. What is important for a CPW transmission line? Like something which is not obvious from the design itself, something you have to do. Exactly. The 2 grounds have to be at the same potential. The things we connect across in order to stitch the ground planes together, which we have not done so far. And that could be a reason that the impedance is slightly off. But I have no idea as of now, because as I said, the calculation model sometimes varies significantly. But we will try that because I want to show you how to draw those kind of structures in microwave office. And we'll see if actually that makes a difference or not. So in order to do that, I'm going to go back.
Sir, after making it the lab, how much it will get?
It will be even lesser, but it won't be off by a lot. So usually there will be a difference between the idealized model and the EM simulation. But your EM simulation should match closer to the your experimental data. Now there are many other factors, right? Whether you have measured correctly. Second is whether the dimensions you have actually tried to design have come out correctly or not, because there are tolerances in the machines which make this. But again, if you're talking about agreement in the level of below minus 20 dB reflection, that has really no meaning because the errors will propagate very easily, especially if you don't calibrate these instruments. So there is another calibration step. This is something we'll learn later in the course on how these instruments make these measurements and why you need to calibrate them. Because when you're trying to measure these very low reflections, you have to be very accurate about it. And you need references to match against. So there are something called standards which one uses to calibrate the system. And only if that is done properly, you can have things matching very well. But we are talking about mismatches of which are not relevant practically. If they are big, then there is some problem with the design. So let me see if I can just undo and go back how it works. Microns, 500 microns. This is what we had before. Now, go back here. Because they're having trouble seeing this. So I'm going to show you two different techniques. The first one is how we actually do it in circuit boards, which we like the one TMM6 material, like the ones I showed. And then I'll show you another trick, which is what is used for smaller chips, like making them on silicon and sapphire, things like that. So for the first one, so I need the ground plane because that's what is we are going to stitch to. Right? So what you need to do is I'm going to zoom in one of these things here. In order to create the via, I have to first basically define a patch of metal where this connection is going to be made. And that's just made by putting some rectangle here. The difference comes in how I define the property of this. So again, the material is perfect conductor. And right now in this thing, so this by the way, I did by right clicking the thing and going to shape properties. So it says EM layer 1, and it's actually showing it as a via, which is what we want. But EM layer 1 is the wrong layer. I have to use EM layer 2. And this suggests that this square I have drawn here is actually like a cross-section square, but it goes all the way from the top of this layer to the ground. So this is what we need. And then we just move this into position here. So these are all microns. Let me go 100 microns into that. And all I have to do is copy this and paste it across on the other side. Copy paste is just because I didn't want to do the whole thing again. If you check the shape properties, it has the same. So what has happened now is this conductor, the top ground plane. Sorry, I made a mistake here. That's the wrong place, not there. This has to go here. So ground to ground, right? So this means there is now connection from that ground, the side ground plane to the bottom ground plane, and this one is the same. So both are now connected at this point across these two things. But you have to do this at some regular intervals along the length of the transmission line. Otherwise, it's like you solve the problem here, but then these two potentials can drift. So the higher the density of these things, the better. But then again, in a simulation, you have to worry about the simulation time. In your real setup, you have to worry about whether how much you can realistically space them. I have made them as 50 micron squares, which is kind of, I guess, small compared to what one typically does, the size of the holes one drills. So maybe better to make it 100. And And then a simple trick is to just copy this. So select both of them, and then you get another one. So we go and let's say nice. Then I usually select all four of them. I have four. Roughly paste them. This one more is good enough. If you now look at this in that 3D view, you can see what's happening. So there are basically connections at all those points on the top there. And if you remember, I told you that if on this 2D drawing surface, if two pieces of metal just touch each other, that means they are in perfect contact. Here we have actually put them on top, so they are assumed to be in contact. Now let's see if this simulation will run. So you see that changed the response in terms of the period of the things, but it's still pretty good. Now the thing we have to see is that if I reduce the width, which is what PX line had predicted, does it get better or not? So I'm going to increase this again for reference. So reduced it from 500 to 400, but I have to bring the ground plane closer. Select the whole thing, and then so we have 400 width now and 100 gap. So it's much better now, significantly better. Now at minus 40%. So those things do make a difference. And typically what you will see is that if you don't do this in a real structure for a very long period of time, you'll actually get a resonance. At some point, you'll actually get reflection because your CPW mode and your slot line mode, energy starts to flow between them. And on the other end, if you have a slot line mode, that is not dominated in 50 ohms. Because the two slot line modes are just actually shorter to each other. So that creates a boundary condition which then leads to a resonance. Yes? So slot line mode is what I told you the other day. It's the type of transmission line which you don't use much. It's this one. So slot line mode is just two metals and the fields are now propagating in the gap. So in a CPW, the two ground planes can behave like a slot line mode if you're allowing them to change their potential with respect to each other. Because what is the slot line mode is that, right? It's the changing of the potential of the two metal planes. That's how you can allow wave to propagate. But in the CPW, you want the two ground planes to be at the same potential and only the center one going up and down, right? But if you don't enforce that, then that mode potentially exists. And then you will get the slot line mode interfering with your main operation. Okay. So this is very crucial, and because I didn't bring the thing, but you saw those in those transmission lines, there were these holes all along the length of the transmission line. Those holes are exactly these connections, and the way they are made is through electroplating process. So there is a metal on the bottom, there is metal on the top. We drill holes, and then there is a special chemical which is coated through that hole. And then you electroplate copper, and then it grows from one side to the other side. And that's how you create the index. So this kind of technique works for circuit boards, and we have a special machine to do that. But in small chips, like the ones we make for our actually superconducting experiments, and there also we make resonators and transmission lines, and we don't want the same problem to happen there as well. But those are made on either silicon or sapphire, and much smaller scale. So 10 micron gap. So you can't drill holes in a mechanical way. There are chemical ways of doing that. But typically, instead of going through the substrate, which is harder to do, you go above the substrate. Okay. And there is a more sophisticated way, which is complicated and needs several fabrication steps, is that you can create what we call air bridges in a lithographic process, versus using a machine which is called a wire bonding machine. It's literally like a sophisticated sewing machine, but where you have a spool of wire, it's like aluminum. You land it on one metal, and the moment it touches it, it puts a ultrasonic energy, and that melts it, and that wire gets stuck there. And then you move the lever arm to take it up to the next side. And you do the same thing, and then after the bonding, it cuts the wire off. So you can create these air bridges. And if you want to simulate that here, all you have to do is change the enclosure slightly and create a structure going upwards. So for that, we have to play a trick here, because right now there is no top layer. I cannot draw anything on the surface. So I'm going to insert an extra layer of air. It's basically a dummy layer. I'm breaking up that air. Just like in a strip line, you needed 2 layers to define a metal in between. And to keep everything else the same, I'm going to make this 1 millimeter each, so that the total thickness remains the same. And now, when I go to the structure here, I have to change the location of this metal. So it has now moved to EM layer 3, because that is where the dielectric is now. This is 1, 2, and 3. Earlier there were only 2, so this was 2. So I have to move this back to EM layer 2 and make a VR connection like this. So this right now actually isn't the full story. This just means that there's now a metallic connection from this dummy or virtual layer in the middle of air down to the surface layer. But in order to complete the connection, I have to put something across. Because earlier the ground plane was serving the purpose of connecting the 2 sides, but we don't have anything to do that right now. So for that, I need to make another metal. So the way you do it is draw one across it like this. So just move it aside here. Go to the shape properties. This one is not a via. It's going to be on EM layer 2, and it's just going to be a conductor. Okay, so it's going to be a layer drawn at that virtual position, but it's not going down. These ones are going down, this one is not. So I put this over here. If I go back to the 3D view, you will see what has happened here. So it's showing this going across, but this one is not showing.
One just below is not changed.
Hmm?
The one which is below you will change that.
Yeah, but that shouldn't have mattered because it's shown one of them. Just a graphical flow. Select all of them. This is also something you can do. You can select all of them and change all of them at the same time.
So all these are copied to the first one, so it will be changes in the first one, the changes to like the.
No, but when you copy paste two different parts in a Word document, change the top part as the bottom part change. They're not linked like that. It's not like it's a reference to that object. It's really, I copied and pasted to save time so that they have the same properties in terms of the EM layers. The problem going between back and Control C versus commands. It's very strange. And just yeah, we'll just run the simulation to see, but I'll just make one fresh mental piece. See that it's probably just some software.
So last time you had to make it included every time you were changing the grid space. So this time also maybe the people will.
No, that's not. Let's run the simulation. You will know whether it's doing anything or not. So what should have happened is there should have been like these metallic links from top to the so we have all of the references. So clearly it has not worked. Its colors have no meaning. guy who wrote this was like me when I was a grad student. There's something I can never forget. I think in towards my end of my first year of PhD, I made my first presentation. I took it to my advisor and I showed it to him. Went through all the slides. I had only one question to ask. So, what's the algorithm behind your color scheme? It took me a minute to even understand what he was trying to ask. It looks good. It did not look good. I had written 10 sentences, each one in a different. Even though I think that presentation was made in PowerPoint, these were the days when we were still using overhead projectors. So we would then print them on laser transparencies. And so I think I gave one such talk or two such talk in my first 2 years. And then everything became this projectors and PowerPoint. But yeah, I can never forget that. And it continued later on. Some years back, I gave a presentation. Most of the people had other comments. He asked me, I think your fonts are too small. Now my students have to face all of these problems. Fine. Just try one more thing. So, Tanya, what were you saying? What was happening last time? I mean, when I was.
Whenever you would go for during the 3D, you would be reading it and reading it again.
Deleting what?
Right. This thing basically. No, not the structure, just the fact that you see the. Like you just cut it and open it again. That's what I'm saying. Just open it again.
You mean just delete it?
Not this. Just where there
Oh,
are
I
tabs.
have already done that like 10 times. So it's not, that's not good.
VI is a solid thing all around, or is it hollow and like pure?
I think it's solid. I mean, probably doesn't matter for this. But you saw that when see when this one was the lower one, I can still do that, right? Because the top layers don't matter. If I change this to EM layer 3, I have this thing.
Sure.
Then it shows up correctly. That's what we saw. Oh. God. Software. It's almost like the software was playing with us and said, well, now it's too much. Let's just fix it. But if I change this back, you think okay. So, show of hands, how many people think it will fix? It will be okay. Somehow, okay. Right. So I guess I have to now move this guy. See, but it's strange, right? It did not do the simulation correctly as well, which meant that it was not connected. Not something. this is what it looks like. So of course, the height you choose for that dummy position depends on what you would think you can achieve in your real setup.
So each of these meter strips is also connected.
Yes. So what we had to do, see, there are only two types of conductors you can define in the simulation. One is on the plane, and another is through the plane.
What I'm saying that those strips you have drawn down. So those strips should also be connected. You have connected only two.
In a case,
Like this.
there are also these streets are connected by the street.
But the graph is still.
Yeah, the graph is not.
horizontal.
Say that again.
Yeah.
So, okay, this is a slightly subtle. I'm going to move this here to make this very clear. Right? So there are three types of metals. There is the original ground plane. Then there is this square, which is a connection from the original ground plane up to this dummy layer. So that's a metal which goes up like this. Then similarly on the other side, and then there is this extra metal layer which I have drawn, which is now on a different layer. It's on this dummy layer, or interface between these two dummy layers, and it's going across. So since they're all overlapping, it basically means that you have ground plane here, then there is this VR patch which goes up, then there is this metallic patch which goes sideways, and then another metallic patch which comes down.
So what I'm saying now, these all patches should be connected, by horizontal metal plate.
But that is exactly what I'm trying to do now.
So I mean, there's can have potential difference from the left side to the right side.
Are you talking about the middle one or the side?
I'm saying that there should be one horizontal.
You mean like this?
Yeah.
Fine. It's already here. See, we are trying to fix the potential of this guy to that guy. That's the purpose of this. Connecting this like this is not going to really make it. It's sort of like I could, instead of having these kind of strips, I could have had an entire metal plane going all the way across like that. So that would be like a full, almost like a ground plane kind of thing. So,
Sir,
yeah.
can you repeat why you have too many like periodic this connection? Why you have this periodic by one?
You can use so many.
Yeah, so many like by one.
As opposed to just doing one.
Spatial.
Oh,
I mean, the very reason we even started doing this, see, at this edge, these two are connected together, right? Because they're forced by this -1. And in a real setup, those will be connected to a metal at the edge, to a connector to which you're launching. So if it is connected here, then why do I have to bother? You have to go back to that one sentence I kept repeating for the first 4 lectures over and over and over again. Defining a potential at one point at microwave frequency has no meaning for the rest of the method. So at this point, the two ground planes have the same potential. But as you go along, their potentials could change because it can support a wave there, right? Because it's a spatial, it's a long distance, it's not kind of a wave. So that's why we are trying to continuously reconnecting them so that they don't drift with respect to each other. That was the point of the starting of the discussion. I'm a little confused that वो कहते हैं ना रामायण सुनने के बाद सीता कौन है ऐसा वाला सवाल
I am saying
है।
that I mean that the period of that. So the continuously connected to it.
Oh, that's a step. Practical thing that you cannot, it's not possible to make such a solid thing in a general scenario. So you do it as frequently as you can. So again, it depends, right? If these are happening much more frequently than the wavelength, then that's basically, so the wavelength sets all the scales here, right? Things change appreciably on the, when you have some fractions of wavelengths away from the original point. So the point here is that you need to, whatever is the relevant frequency of operation for that frequency, you have to think about the wavelength and then put these at distances which are maybe, I don't know, a tenth of wavelength or so. So then that way you know that things cannot change so much from this point to this point. But you are right that in the ideal thing would be that it's continuously stitched, but that's not practical when you are making these things. So you can't have that many BRs or can't have this kind of stuff. That's why you do it as much as possible. Now, but the bigger mystery here is why this is not doesn't seem to be doing anything.
So can you please draw that horizontal strip horizon and see that?
Right, let's do that. So I have to make sure it's the right location. So it's after. Let's verify this. I say it will not make any difference. Who dares to go against me? He's already gone against me. He's confident, sir, kar dijiye to sahi ho jayega.
Maybe it is like the
Anybody else?
previous thing is following up now. Like everything is a little late, right?
तुम कह रहे हो कि कुछ भी करो वो धीरे-धीरे वो ठीक हो जाएगा. So
The situation looks like this is continuous, just like it's not. Yes.
sorry, say that again.
Like we use this horizontal strip. So does it look like it is continuously switched or does it?
No, it's not the same as what he was suggesting because you need that thing to extend from both sides, right? Just by adding an extra strip. Because we are not trying to, so let me explain why it doesn't make any difference. See, we are not trying to equate the potential of this point to this point. That's not the purpose. And that's what this strip is going to do.
Yeah.
We want to make sure that the grounds on either sides are always the same potential. Because the moment the grounds can change their potential, it allows the slot line mode to proceed. So the main purpose of doing this is to suppress the slot line. So this doesn't help. What can help is, so let's do what he was suggesting. The simplest way for me to do that is to just stretch this code. So I've just extended that same object all along here. So it's now a continuous long object, but it's also going down. And then similarly, I will take this guy. So I'm not going to bother removing the other ones because it won't make a difference. So this is what he wanted. So now we have a complete enclosure like that. So, by the way, we are still talking about small changes here. This is all still below minus 20 dB, but what we are trying to compare is this curve we got for when we went through the ground. And we're trying to see if this is looking similar to that one. This might be a little slower. It's behaving slightly strangely. I'm not sure what's happening. I'm going to try one more thing. Maybe the okay. Clear the previous ones. Please this one. I have a feeling these paths are too long. So this is another thing one has to notice, which I didn't mention before. There is a conductor which is going up, across, and down, right? Now, what should be the length of that conductor? Ideally, as short as possible.
That will have some path.
Exactly. So it has basically this kind of size scale. We will say that that's an inductive connection, right? The lower the inductance of that connection, the less the potential difference you can have across it. So what you really want is a true short circuit, which of course doesn't exist. So you want to make it as close as possible. So having a solid line like the one we did before does create that effect. But maybe given the dimensions here, so this is a 50 micron gap, right? And no, sorry, 100 micron gap. And this is 500. But my air block was 1 millimeter, the virtual boundary. So it's 1 millimeter up, about 500 microns across, and 1 millimeter down. So it's actually a very long path, 2.5 millimeters for this kind of thing. Maybe it's too high, too big, too inductive. So the simplest thing to do here would be to reduce the thickness of this guy and make this 1.9 so that the total thickness remains the same. See if that sort of fixes it, right? So this looks sort of reasonable, but here there is a potential problem. Because the gap here is about 50 microns. This height is 100 microns right now. So this is going to now feel the presence of the ground plane because of the this connection as well. Not so much. If it was continuous, it would be even worse. Won't bad. The thing is, you just have to retune the dimensions because this will now have a different capacitance per unit length as well. So it's doing two things: stitching the ground, but is also adding some additional capacitance to the ground as well, and that could potentially affect it. Let's see how that changes. See, this was not the case for the one going down because the ground plane always existed, right? So here we have put another ground plane. And somehow it doesn't make. Okay, I have to admit I am not 100% sure what's happening here. So I will look at this and maybe explain this different class. Okay, but point is, this is how you make these air bridges. So that part is clear.
So, this is what we use.
Sorry?
Zoom.
Oh, I haven't done that yet. Okay, for the last 3 lectures, I'll do that. Okay, maybe I'll just tell you one other short thing before we go. And that is about using these EM structures as part of a different simulation. Right? So, for example, let's say that the EM structure you were designing is a quarter wave transformer. So, just to use as a reference, it's the microstrip one. It really doesn't matter which one. And let's create a scenario where we want to transform 30 ohms to 50 ohms, right? So, what's the formula? Can someone tell me what is the quarter wave transformer impedance should be? It's 50 into 30 square root, right?
50 square by 30.
Maybe. That's not. I want to match 30 ohms to 50 ohms. So I want to know the transmission lines. That's just the geometric mean of the. So it should be about 38.7. That means a width of 1800. I want 90 degrees, so that's physical length of 3450. So 3500. Let's go here. So 1.1. This was 25. So I need 3.5. So I've just made a quarter wave transformer, and I've chosen a center frequency of 10 gigahertz. So actually I should change this frequency range here. 8, 12. Yeah. So obviously the transmission reflections are not so great because this is not a 50 ohm transmission line. But I want to test this as a impedance transformer. So when you in the measurements, when you choose the name here as the EM structure, the ports refer to the ports which are connected on the EM structure itself. Okay. But now I can create a schematic where I can bring this EM structure as an object, which has already been, if it's been pre-solved, it will just won't have to solve it again. So you go here in your elements, right at the bottom, there is this thing called sub-circuits. So these are all the circuits which you have created, including schematics. So if you have a schematic with 5 ports, it will show up as an object with 5 ports, which you can call in another schematic. So you can really use them as modules in one another. So here I'm interested in the microstrip subcircuit, which is the, so it's just by the name, it doesn't know whether it's an EM structure or anything like that. And it again gives you the same 2 ports you have created. So here, of course, they are completely symmetrical. So, and these are port connections. So in order to run the schematic, you have to put a physical port on it. So we're going to put a port here. And we're going to put a load here. So what was the load I said? I wanted to match to 30 ohms, right? So here, bring this load and set this to 30 ohms. And now we have to find new graph, and we'll just plot S11 of how the schematic. So this is important that you choose the right thing. Schematic, magnitude. There's only one code there. So it's this one. So you see that the reflection goes to a very small number. It's not exactly at 10 gigahertz because there's probably some difference between the TX line and the. This here is lowest point where the reflection is very small. So that's where you're getting the matching as a quarter wave transformer. We can look at one very big thing here, which is the microstrip one. We disable the reflection and instead look at the phase of the transmission. See where it's 90 degrees. So, yeah, so in this actual simulation, it's 90 degrees is around 9770. And here, okay, it's not that. So maybe the transmission, the impedance itself is also not perfectly correct. So we could try something.
So
Yeah.
there is this.
Oh. Yes. I'm just going to make this impedance tunable because maybe the what is predicted by the TX time is also not the characteristic impedance of the transmission line. So we just check this to see if there is a better matching at a different impedance. So slightly off, but for some reason the frequency is not changing that much. So this is giving me a quarter wave transformer at 9.4 gigahertz, whereas the transmission curve is something like so this could be due to some inaccuracies in the EN simulation. So you can try. So maybe you guys can try this at home and see what happens if you change the grid size, increase the resolution, see if you can make this to match better. That will tell you what's going on. I'll also check this to see what's going on. Okay, so let's stop there. And since I'm traveling and the next Monday is Diwali, so there will be no class on Friday and Monday. I'm going to check your timetable and see if we can have some extra classes after that as well. Yeah.
So about that, we are seeing.
Yeah.
So there are two things. Do we want the potential to be same throughout, or like it can't be, right? The length is changed as the length changes.
Throughout, you mean in
like the port 1 minus 1, we want in that.
in this direction?
Yeah, that's not a concern. Right?
No. Well, that you cannot anyway, right? Because I mean you could, but there is going to be a finite structure involved. The idea is to make sure that the either sides of the ground planes always
So that
don't shift too much.
Can we see the part where you said we don't use gears, it acts as a slotted and rest of the function.
So, if a slotted line mode is allowed here, then it doesn't look like a transmission line with matched boundary conditions on either side. So, multiple things happen. One is that your energy will convert from the CPW mode into the slotted line mode, because This is like all the different excitations. The excitation in the CPW mode also behaves like an excitation, a partial excitation on the slot line mode. And then that can convert. And then in the slot line mode, there are reflections on either end. See, a CPW mode wave will encounter 50 ohms at either end. So once it hits that, it cannot reflect. But the slot line mode is going to encounter a short circuit because the two ground planes at the end are connected to each other. So that looks like a length of transmission line with two shorts on either side. So then you can get things bouncing back and forth, and you will also have energy converting between the slot line and CPW and back. So you will get some weird resonance because of that. So that's the reason you have to suppress it.
So then we can say the current factor of the CPW is more than the slot line. That's why maybe we don't use it much the slot line.
The quality factor.
Yeah, presumably resonances.
Resonances here is entirely due to the boundary condition. It has nothing. Quality factor has got to do with the loss in the transmission line due to either the metal or the substrate and all of those things. At the level of these simulations, there is no loss. Everything is ideal, right? Now, for a given transmission line, whether a transmission line made out of slot line mode or a CPW mode, which one will have less or more losses? That's a valid question. But that's not really why we don't use slot line modes that commonly. It's just not a very convenient way to transform from one to the other. This differential excitation. In some cases, they are useful. And a slot line can also be thought if you bring in a third conductor, like we had looked in the case of the coupled microstrip line, this one. Right. So if I forget this ground plane, then that looks like a slot line mode. So what is that slot line mode in this picture? It's the odd mode. Because remember, the even mode goes like this. Both the plates together, and the odd mode goes like this. So the odd mode is sort of like a slot line mode, and it's a more controllable, easy to connect to in terms of external interfacing. But there are situations where slot lines are actually used because of. Remember, if we were trying to calculate the impedances, we saw that we were not able to get a 50 ohm slot line. So it has a different range of impedances which are easy to realize. So you can, in some cases, you make resonance structures which are part of an overall circuit. Use a slot line like that. That is important for creating the overall response. And you have transitions from CPW to slot line or microstrip to slot line. This is something I think we will look at later on when you go from one type of transmission line to another type of transmission line. How do you make those changes? Sometimes you use slot lines deliberately to get those resonances for certain structures. I remember one example, but I'm not able to remember what exactly that device. I will look it up.